So, the last presentation of this afternoon is entitled Wave-Based Chemical or Biological Microsensor for Environmental and Health-Related Applications. And it is presented by Corinne Dejous, who received a PhD degree from the University of Bordeaux in 1994. She became associate professor at the University of Bordeaux in 1996 and full professor in 2009 at the ENSERB Matmeca. She is the director of the Department on Embedded Electronic Systems from 2013 to 2018. And her research field is on about acoustic waves, chemical microsensor, and wave-based resonance sensor. She co-authored over 80 publications in journals and books chapter, and co-supervised 35 research projects. She is involved in the French chapter of the IEEE Sensors Council, and now it's yours.
Thank you for this detailed presentation. Thank you also for inviting me. I will try to skip a few slides to let you have time to visit Bordeaux then in the evening. I propose to show you a few studies that are going on in our team at IMS laboratory. So based on chemical and biosensors, chemical sensors and biosensors mainly. So we are in a group which is called WAVES, because all our devices are based on resonant devices or waves in general, and especially the new organization with the 3 topics from materials, devices, and the new topic related to zero power devices. We will have a few introduction about that. First, a short introduction about chemical sensors. When we call about chemical sensors, we have to deal with not only the sensor itself, but we have to deal with the full context, the full platform going with the sensor. I try to get the mouse. I don't know. Yes, it is there. The transducer, but we have to take care about what we want to analyze, of course. Which type of compounds, what is with this compound that we don't want to detect, and also all what is needed to get to an information that can be used, and also with the energy related to the powering for this platform. Many applications, of course. I guess you know some of them in each of your devices and studies and the works. And so, as I said, from the beginning, if we want to work on this platform, from the beginning, we have to define, identify the application area and the context of our device. Then we want to get a converter, a transducer, with different types of technology that can be involved in this transducer. We will focus on one of them at least, and another one perhaps dealing with the resonant device. This transducer, I have to show. This transducer will be able to convert typically either a mass effect, viscosity change, conductivity change, some parameter into an electronic signal. But most of the time, we have to add an active layer, what is called there an active layer, which will have as a role to emphasize the sensitivity, the selectivity towards some specific compounds that we want to detect. It can be some chemical targets, it can be some biological ones, and we have also to take care of all what can influence these sensors in terms of temperature, humidity, and many things that we would not want to detect. And finally, at the end, the overall sensitivity is taking into account all these sensitivity when the chemical or the biological target is immobilized or interacts with the active layer. There is a first level of sensitivity, namely a change of mass, viscosity, and things like that. And the transducer itself can be sensitive in a different manner with each one of these parameters, in fact. And of course, the third level of sensitivity is the electronics that we can add to that. So wave-based devices, because we are using most of the time resonance system, and I will focus mainly on acoustic platform that we have been working on it for many years now. So based on a piezoelectric substrate. We will perhaps have a short time to speak about an electromagnetic platform too on a flexible substrate, sorry. Yeah, and that's it, but it can be applied to other types of device in terms of wave-based device, in fact. So the source sensor principle, maybe you already know some basics about that. Just you can see something that is moving. It is a vibration, mechanical vibration that is involved either in a bulk piezoelectric device, such as the bulk wave transducer, with a vibration that can be parallel to the surface or vertical, perpendicular to the surface. Depending on that, we will have different types of sensitivity, in fact, depending also on the medium, either a gas or a liquid. And if we want to go towards some even more sensitive devices and with the possibility to have collective fabrication, we go to surface acoustic waves, such as the surface wave transducer. The basic principle is, and the primary interest is that we can confine the density of energy of the vibration at the near surface of the interface, and in order to be very sensitive to what happens at the surface, in fact. This type of surface acoustic waves can be, can be generated on a quartz substrate or a piezoelectric substrate dealing with piezoelectric effect, inverse and direct here, so that we can get a vibration like that. And then if we want to provide chemical sensors, so in fact this can be integrated a lot, of course, it does already exist. On our side, we are going to make our own devices so that we can have place enough to put our active layer and make it sensitive to the target molecules that we want to detect, and then have good understanding of what happens on this layer and the results in terms of electrical characteristics, such as change in the resonance frequency and also in the magnitude of the device. So this is an example of collective fabrication that has been made typically by the last NRS in Toulouse. And we also use some typical wave, such as Rayleigh wave, and most of time now based on the Love waves that have been proposed by Mr. Love. And the main principle of this type of wave is to use some mechanical vibration that are parallel to the surface and perpendicular to the propagation direction, so shear horizontal surface acoustic wave, because the layer with the red part is a guiding layer that is able to trap the overall energy from the piezoelectric substrate in blue and to make it propagate at the near surface. By doing that, we have a very good sensitivity, and by the fact that it is a shear horizontal waves, we can also work in a liquid medium. This is an example of modeling and simulation to get an optimized device in terms of crystallographic angle, cut orientation of the quartz, for example, in this case, and also of the thickness of the guiding layer, which is made of SiO2. Then, of course, typical characterization with a vector network analyzer and the resonance frequency and the linear phase that make it possible to make, for example, an oscillator based on that. And due to the deposition of a sensitive coating and then to the immobilization on the interaction with some target molecules, target compounds, we have a variation of the amplitude, the magnitude, and of the phase that can be expected and that can be measured, in fact. On the temporal, the time domain, we will use it in some cases. Here, when doing a FFT, Fourier transform, we can see the acoustic wave at few microseconds. And in some cases, we also have an electromagnetic wave that is propagating directly, very fastly, compared to the acoustic wave, from the input to the output. And we are also able to use it in some cases, but I hope I will have time to talk about that at the end, perhaps. So the readout electronics, it can be either a closed loop with an oscillator configuration or an open loop based on a direct digital synthesizer. And few applications that can be in gas or liquid media, of course. Some typical applications are also to characterize some thin film or so complex fluid with some viscosities, for example, that can be on the devices and that influence the wave propagation. So it's also a way to real-time monitor some variation in a surface layer, for example. So the sensitive coating is of primary importance. The material, the deposition method, the structuration, and of course the result will depend on all that. So this is our first very old now results, one of the first that have been put to evidence about very toxic gas, for example, for the army. This is the sarin. It was made with a layer of specific polymer that has been developed in order to emphasize some hydrogen interaction which confer a good compromise of the sensors in terms of sensitivity and reversibility at the same time, which is something that we always have to do. We can get a very good sensitivity, but poor reversibility, or the contrary. In this case, we wanted to get something that could be reversible, but also quite selective and sensitive. So this polymer could allow to obtain such type of curves, which was quite interesting. And we also could emphasize the sensitivity, for example, by using spray coating, which is a way to get a quite high effective surface, in fact, instead of getting a very planar sensitive coating, which could limit the effective interaction surface. In fact, this is another way with some other people in chemistry that were developing some mesoporous materials with a lot of pores inside. It is another way to get good effective surface area, for example, and with also another advantage, which is good stability, thermal, mechanical, and also chemical stability. So like that, we have investigated a lot of different types of material, in fact, each time with different teams. And as a last example for this gas application here, this is a graph that is representing the using of graphene as sensitive material. So this graphene that is represented here, and that is compared to other, so in blue, and it is compared in terms of sensitivity to a particular concentration of some particular gases. It is compared with some mesoporous silica, for example, some molecularly imprinted polymer, and other things like that. And we can see that we could get high sensitivity in blue with the graphene. Why? In fact, two reasons. The first one is that we can get a lot of active sites to interact with some target molecules. But there was another effect that we could discover and use with such materials, is the fact that it is a 2D materials, in fact, that has the advantage to have a very good mechanical characteristics in terms of elasticity. And thanks to this layer of graphene, we could enhance the wave propagation along the substrate, in fact, the surface, and it allowed to get a better result of the device finally at the end, due to this mechanical elasticity, which was not expected at the beginning. Then going to liquid application. For liquid application, we had to localize the liquid in the first approach, at least, in order to avoid the liquid to be in contact with the electronics, of course. So we tried many manner of polymer chip in order to localize the liquid and make it flow where we want on the surface. It was also a way to use very small quantities of liquid, of course. We started by characterizing the response of the device due to some mechanical parameters such as viscosity and also electrical parameters such as conductivity. Of course, we have a mechanical device which is very sensitive to mechanical parameters, and so we found what was expected, which is high sensitivity to mechanical parameters and a low sensitivity to the electrical parameters, which allowed us to go into some applications for liquid media, still based on the same effect. So the deposition of an active layer, the first one that we have tried was classical one based on antibodies finally, that we had to deposit in an appropriate manner on the device surface with a link layer. And also, so antibodies have the particularity to have specific sites for binding with antigens here. And all the rest is quite classical and quite identical with different antibodies. So we could get a way to deposit them in an appropriate manner with the link layer, but we had to block the non-specific sites of antibodies by using a saturating agent, in fact. And then it was okay for detecting in real time, in this case, bacteriophage, which is a virus for bacteria, in fact. And so we had some results with that. Based on the first results, we went into detecting some bacteria. So, for example, on these curves, we have a real-time response again, while depositing the layer of antibody, depositing the saturating agent, and then detecting the Escherichia coli bacteria. And you can see that we have a sensitive line and a reference line, a reference channel, where we could see that we could not so much detect, in fact, so it was a sign that it was working properly. Based on that, we could make some detection. The fact is that detecting by using some antibodies and things like that is quite difficult, very expensive. And so we had the idea to try some other way to go towards more easy ways of detection, of using some detecting agent. And one of them came from using some whole cell-based biosensor. And in the case of, for example, heavy metal detection or some other pollutant, we are some human beings, so living people, and we are sensitive to some pollutant detections. And it's the same for bacteria. It's the same for algae, for example. And so we try, instead of using some very expensive and some compounds that have to be synthesized with very heavy chemistry and biotechnology, we try to go towards the use of such bacteria, for example, in this case, and we have made the same with some algae, by using these bacteria as sensitive material to detect some pollution. And so we can see the real-time detection, the real-time realization of this sort of bed for bacteria, so that they can be easily attached on them in an appropriate manner. And we can see in real time the left figure, the deposition of each layer. And then on the central, the medium figure, we can see the detection of cadmium. We could see also the same with the detection of mercury, for example, at very, very low concentration, such as 10 to minus 12 molar concentration, which is very, very low. And so we were quite happy to see that it could work. I could come, if you have some question, on the fact that we have an increase of the frequency and not a decrease, which has been a great question for a few months and even a few years, perhaps, but I will come back to that later if we have time. We could verify that the bacteria were there and were not in good shape when we had some pollution, in fact. But the sensor is able to see that in real time. And the last slide on this first part is following the previous one. We found that bacteria, it's okay. Algae, it was okay too. But we wanted to try to get something that was natural, a sensitive material, but which was also more easy to use and also more stable, in fact. A great problem of sensors is the stability. And thinking of that, our colleague in Tunisia that was cultivating algae proposed to use some polymers, which are called extracellular polymeric substances, EPS, that are some polymers that algae release in their culture medium. So you can see the culture medium of algae here. So they release some polymer like that we are able to collect, filter, and we get a powder made of this product. And these polymers are used as sensitive material, in fact, on the device. And this, depending on the type of algae, we have different behaviors towards different pollutants. It can be for heavy metals, as we have tried to do, but it can be also for microplastic, for some pesticides, for example. And we could organize 2 workshops in French Guiana and in Tunisia a few months ago in order to get some people involved and used to manipulate such devices, in fact. Perhaps I skip this one to get a little bit faster. I would want to introduce this part to try to illustrate some new approach that are less conventional. So the part with the natural polymers were already a little bit innovative, perhaps, but I would propose to introduce 2 or even 3 propositions that we are starting to get involved into this approach. One is to use what we have called an enriched approach of a single SAW device. So a classical approach to get some very specific devices to measure things in chemical or biological fields is to go towards multi-sensors, a lot of sensors, a lot of data processing, and try to get some information, because it is very difficult, impossible, to get a very specific sensor which is able to measure with a good quantification every type of compounds that we would want to detect. And even we could do that, if we could do that, we would have to develop a new sensor for each application. So the most common approach is to get a lot of sensors and a lot of data processing. Instead of that, so of course it can be a way, and I will show a few examples in the second point. Of course, it can work like that. It can be a way. But the first one that I would like to propose is coming from the fact that each time we have a device, most of the time we use only a part of the information. And we would like to try to open the eyes and try to get the maximum information from a single sensor, instead of developing many ones, trying to get the maximum information from a single one. It could reduce the energy that is needed. It could reduce a lot of things. So this first approach has been developed with our colleagues in French Guiana from the SAW sensor that I showed you. And so the conventional approach that I explained just before is related to the acoustic wave that is generated and propagating from the input to the output with resonance frequency. Dealing with that, I said you that we had to deposit, to localize the liquid medium just between the input and the output interdigital transducers in order to avoid what? In order to avoid getting the liquid in contact with the electronics. But in our sensor, we already have a guiding layer that is made of silicon dioxide. So the IDTs are already protected, in fact. And what? Yeah, it's maybe better with that. I don't show. Yeah. And it is difficult to localize this liquid medium such like that. We wanted, by doing that, to avoid capacitive effect between an electrically conductive liquid there with the interdigital transducer that are here and here. So for 20 years, we worked like that. But in fact, we can put some liquid here. We have some electromagnetic coupling. We also have an electromagnetic coupling that can be through the conductive liquid from the input to the output. If we do that, the curve that we observe, instead of the green one, we get this one, which is difficult to use, to analyze. But thanks to Mr. Fourier, and also as I talked about the temporal domain, the time domain, the acoustic wave is propagating something like 10 to 5 times slower than the electromagnetic wave. And so we are able to go into the temporal response, the time domain. And we have the first part very close to 0 microseconds that is related to electromagnetic wave that we are able to digitally extract and focus on that with the time gating. Then we get this spectrum after temporal window and back to the frequency domain. And we get this electrical signal with the electromagnetic coupling between the input and output IDT still in the transmission response. Then you are using another time gating, focused on the acoustic wave, which is at something like 3 microseconds. And after going back to the frequency domain, we get the nice curve that we were used to have, in fact, without any electromagnetic coupling. And in this case, we recover the focus on the acoustic wave propagation and so the mechanical interaction. Thanks to that, so we also can have some echoes in some times. Maybe it's not a problem. And so by doing that, for example, in Amazonian rivers, Amazonian water, we have some very turbid waters, in fact. And the conventional sensors to get some information from waters is based on optical sensors. The problem is that with a solution like this one with a very high turbidity, the optical sensor cannot see anything in fact. Thanks to the acoustic devices, and by using this, what is called here long chamber, we can put some liquids both on the acoustic path and above the IDTs, and we make the time gating that I just explained, and we can recover the time gating transmission response as here. By doing that, we have an information of the mechanical sensitivity. So any mechanical change that could be due to the detection of a target compound, for example. So it is the first point. And the second point is that we can get the electromagnetic wave that can also be seen on the reflected parameters at the input, for example. And in this case, we can have an information of the turbidity because the turbidity is directly related to the electrical conductivity. And by doing that, our devices is able to overcome the limitation of the optical sensors with both using the reflection parameters for the electrical information and finally the turbidity of the device. And by using the mechanical information in the transmission response with something that is related to the usual device, in fact, for the detection of some target compounds. For example, so it's a way to open the eyes and to get more information with a single sensor, the same as before, but looking at several information, in fact. So this is a part of a larger project to go towards sensor networks for such areas, in fact. The second part that is trying to go into the in-field devices is based on a microwave sensor. For this part, it is not a liquid but a gas application for air monitoring, air pollution monitoring. And in this case, of course, yes, we are using also machine learning or artificial intelligence in order to go towards the in-field application, which is not so easy if we are not doing that. This microwave-based gas sensor is represented here, so with two resonators, still one as a reference and another one as a sensitive resonator. So with the microstrip resonator on hydrophobic Kapton surface that is represented here. Also the test vehicle to characterize the sensors. We can see the resonance frequency on the curves there, either as reflection parameters S11 and transmission 1. And we can see lab experiments by using a series of steps of humidity and also a series of temperature. This is possible to do that in lab, but at the end, we do not have control atmosphere by just changing the humidity, the temperature, and things like that. We have to go to the field and with a set of sensors again. So again, to go to the field, this could be used thanks to our partner, which is Sensity near Paris, Gustave Eiffel University, which offers some very interesting characterization setup, in fact, with a control outdoor or control environment inside a large climate chamber. We could put a set of sensors, and it was also compared to a series, an array of reference sensors for humidity, temperature, and some typical vapors. And by doing that, we could not recover such nice curves as we had in the lab, of course. So in this case, we had to use some nice algorithms in order to get the information, especially because also the concentration of the vapors that we want to detect are most of the time very few concentration and concentration changes compared to some large variation of humidity or things like temperature, for example. And so by doing that, again, it was possible indeed to define which type of sensitive material and sensors should be kept in a set of sensors in order to, so one of them was more sensitive to humidity, one other more sensitive to the temperature without being sensitive too much to the other parameters, and a third one showed some secondary effects towards ozone in particular. And so the algorithms allowed us to choose which sensors were the most effective finally to define the sensor array with these three specific sensitive layers, in fact, that had been developed. And I will finish with this third part, which is talking about towards zero power devices, because we have to take care of energy, of course, again. So the first good point is that dealing with resonant wave-based devices, we are close to the possibility to use some wireless thing, and even most of the time passive components, in fact. Then we have to have a good readout approach for these passive sensors. And so we are trying to look at some solutions for microenergy, and especially with Simon, which is in the lab also, trying to have a deep look towards backscattering approaches that are able to read some passive microsensors wirelessly, in fact, most of the time. And this is just an example of some works that is developing by using possibly implanted biofuel cell, so which is possibly providing some microenergy from glucose inside our body. And then by using some self-powered implantable chip, thanks to this small amount of energy, it is possible to wirelessly communicate with outside of the body and get the information about the glucose. So this is just an example. And in most cases dealing with this backscattering approach is a fan of using some nonlinear devices, especially based on a tunnel diode, which the possibility to use this specific nice part of the tunnel diode in order to make a lot of things, amplifier, mixers, and also trying to get, for example, some energy from an antenna at a particular frequency and backscatter some energy at dual the basic frequency, the fundamental frequency, for example. That is a way to separate the received and transmitted and received backscattered wave, in fact, in a readout system. So I will not go deeper inside that. I'm not the most appropriate to do that. Simon would answer better than me for that. And so just to finish, about the fact that these types of domain about chemical and biochemical sensors is very rich and in relation with a lot of teams all over the world for many domains, in fact, which make it quite difficult, but also quite interesting. And I will finish by thanking you for your attention.
Thank you, Professor Dejus, for this really interesting presentation. So do you have any question in the audience? Yep.
So you use PDMS as materials to create your chips?
True, for the microfluidic part.
Yeah, so how do you deal about the fact that PDMS was well known for being porous, so about being able to capture some chemicals and then to return them for after that?
When we are using PDMS, we are more or less confined to laboratory experiments by doing that. When we are going to in the field devices, we are not at this point yet, but it would be more easy to avoid using anything finally. And as I try to show, now we can have some liquids above the full part of the device finally. So maybe we will not need at the end the microfluidic chip perhaps.
And do you know any other materials that can be used other than PDMS?
I'm not so much used to that, but we can think of other materials. But the best thing would be to avoid using any materials just by placing the device inside the liquid, perhaps. But it can be useful to get depending on the application. If we want to work with very small volume, for example, in this case, it's better to get some microfluidic chamber to try to get just a drop of blood, for example, and things like that. Yeah, it has to be thought depending on the application, perhaps. Do you have some other types of material that could be used? Yeah, it's not so easy. And even when we have to localize just between the input and output IDTs, because then we have to get some air cavity above our transducers in order to avoid absorbing the wave. The mechanical vibration would be absorbed if we have any absorbing materials on the wave generation part finally. So we have to have some very, very small walls of a few dozens of micrometers. And as we want to keep the access to the surface, we also want to put it just by pressure, maintaining it on the device, and that without any leakage of the fluid. So yeah, it's quite tricky.
We have enough time for a last question. Just one question for me. Do you have any success story about industrial integration of a SAW sensor, or is it only prototypes and lab conditions testings?
Some sensors have been commercially produced, but I'm not sure they are really used in the world. Maybe mostly the bulk acoustic wave, a little bit more used, but perhaps more in lab condition. And that's why we are working with the French Guiana, because Olivier Tamarin, that is coming from our team, really wants to develop that for in-field application. And so the fact that we have organized this workshop and support workshop, the aim is that, in fact, to try to get people involved and using these technologies. It's the same as with doctors that are afraid of using some devices if they are not used to what is behind, in fact, perhaps.
Okay. Thank you again, Professor.
Thank you also. Sorry for the difficulty to manage the mouse.
Alors, merci.